Transition and intertransition elements. Exercise pages 190 to 191. Exercise Q 1.01, page 190. Choose the most correct option. Which one of the following is dimagnetic? 1. Cr2 plus. 2. Fe3 plus. 3. Mn2 plus. 4. Zn2 plus. Solution. Zn2 plus. Exercise Q 1.02, page 190. Choose the most correct option. Most stable oxidation state of titanium is _ 1 plus 2, 2 plus 3, 3 plus 4, 4 plus 5. Solution. Most stable oxidation state of titanium is +4. Exercise Q 1.03, page 190. Choose the most correct option. Components of nichrome alloy are _ 1. Ni, Cr, Fe. 2. Ni, Cr, Fe, C. 3. Ni, Cr. 4. Cu, Fe. Solution. Components of nichrome alloy are Ni, crossing. Exercise Q 1.04, page 190. Choose the most correct option. Most stable oxidation state of ruthenium is _ 1 plus 2, 2 plus 4, 3 plus 8, 4 plus 6. Solution. Most stable oxidation state of ruthenium is +8. Exercise Q 1.05, page 190. Choose the most correct option. Stable oxidation states for chromium are _ 1 plus 2 plus 3, 2 plus 3 plus 4, 3 plus 4 plus 5, 4 plus 3 plus 6. Solution. Stable oxidation states for chromium are +3, +6. Exercise Q 1.06, page 190. Choose the most correct option. Electronic configuration of Cu and Cu1+ are _ 1. 3d10-4s0, 3d9-4s0. 2. 3d9-4s1, 3d9-4s0. 3. 3d10-4s1, 3d10-4s0. 4. 3d8-4s1, 3d10-4s0. Solution. Electronic configuration of Cu and Cu1+ are 3d10-4s1, 3d10-4s0. Exercise Q 1.07, page 190. Choose the most correct option. Which of the following have D0S0 configuration? 1. Sc3+, 2. T4+, 3. V5+, 4. All of the above. Solution. All of the above. Exercise Q 1.08, page 190. Choose the most correct option. Magnetic moment of a metal complex is 5.9 bm. Number of unpaired electrons in the complex is _ 1, 2, 2, 3, 3, 4, 4, 5. Solution. Magnetic moment of a metal complex is 5.9 bm. Number of unpaired electrons in the complex is 5. Exercise Q 1.09, page 190. Choose the most correct option. In which of the following series all the elements are radioactive in nature? 1. Lanthanides. 2. Actinides. 3. D-block elements. 4. S-block elements. Solution. Actinides. Exercise Q 1.1, page 190. Choose the most correct option. Which of the following sets of ions contain only paramagnetic ions? 1. Sm3 circle plus, Ho3 circle plus, Lu3 circle plus. 2. La3 circle plus, Ce3 circle plus, Sm3 circle plus. 3. La3 circle plus, Eu3 circle plus, Gd3 circle plus. 4. Ce3 circle plus, Eu3 circle plus, Yb3 circle plus. Solution. Ce3 circle plus, Eu3 circle plus, Yb3 circle plus. Exercise Q1.11, page 191. Choose the most correct option. Which actinoid, other than uranium, occur in a significant amount naturally? 1. Thorium. 2. Actinium. 3. Protactinium. 4. Plutonium. Solution. Thorium. Exercise Q1.12, page 191. Choose the most correct option. The flux added during the extraction of iron from hematite is its 1. Silica. 2. Calcium carbonate. 3. Sodium carbonate. 4. Alumina. Solution. Calcium carbonate. Exercise Q2.01, page 191. Answer the following. What is the oxidation state of manganese in? Solution. Exercise Q2.01, page 191. Answer the following. What is the oxidation state of manganese in? Solution. Exercise Q2.02, page 191. Answer the following. Give uses of KMnO4. Solution. Uses of KMnO4. I. Used as an antiseptic. E. Used for unsaturation tests in the laboratory. E. Used in the volumetric analysis of reducing agents. IV. Used for detecting halides in qualitative analysis. V. Used as a powerful oxidizing agent in the laboratory and industry. Exercise Q2.03, page 191. Answer the following. Why salts of Sc3 circled plus, T4 circled plus, V5 circled plus are colorless? Solution. I. Condensed electronic configurations of Sc3 plus, T4 plus, V5 plus are Sc3 plus, Ar3D0, T4 plus, Ar3D0, V5 plus, Ar3D0. E. The ions Sc3 plus, T4 plus and V5 plus have completely empty d orbitals, i.e., no unpaired electrons are present. Thus, their salts are colorless, as DD transitions are not possible. Exercise Q2.04, page 191. Answer the following. Which steps are involved in the manufacture of potassium dichromate from chromite? Or, solution. Preparation of potassium dichromate. In the industrial production, finely powdered chromite or FeOCr2O3 is heated with anhydrous sodium carbonate, Na2CO3, and flux of lime in the air in a reverberatory furnace. Exercise Q2.05, page 191. Answer the following. Balance the following equation. Solution. Exercise Q2.05, page 191. Answer the following. Balance the following equation. Solution. Exercise Q2.06, page 191. Answer the following. What are the stable oxidation states of plutonium, cerium, manganese, europium? Solution. The stable oxidation state of plutonium is +4, cerium is +2, +3, +4, manganese is +2, +7 and europium is +2, +3. Exercise Q2.07, page 191. Answer the following. Write the probable electronic configuration of chromium and copper. Solution. I. The probable expected electronic configuration of chromium is 1s22p63s23p63d44s2 or Ar3d44s2. E. The probable expected electronic configuration of copper is 1s22s22p63s23p63d94s2 or Ar3d94s2. Exercise Q2.08, page 191. Answer the following. Why nobelium is the only actinoid with A+2 oxidation state? Solution. I. The electronic configuration of nobelium No is Rn 5f146007s2. E. After losing 2 electrons, No forms number 2 plus ion, which is stable due to completely filled 5 orbitals. E. Such extra stability due to completely filled orbital is not acquired by any other actinoid in their +2 oxidation state. Hence, nobelium is the only actinoid with A+2 oxidation state. Exercise Q2.09, page 191. Answer the following. Explain with the help of a balanced chemical equation, why the solution of CeIV is acidic. Solution. I. According to Lewis acid theory, a species that can accept a pair of electrons is an acid. E. The electronic configuration of Ce is Z4F15D16S2 and that of CeIV is Z. E. CeIV can accept lone pairs of electrons from water molecules in its vacant orbitals to form the complex. Hence, the solution of CeIV is acidic in nature. Exercise Q2.1, page 191. Answer the following. What is meant by shielding of electrons in an atom? Solution. I. The decrease in the force of attraction exerted by the nucleus on the valence electrons due to the presence of electrons in the inner shells is called the shielding effect. E. As a result of the shielding effect, the effective nuclear charge experienced by the valence electron is less than the actual nuclear charge. Exercise Q2.11, page 191. Answer the following. The atomic number of an element is 90. Is this element diamagnetic or paramagnetic? Solution. The electronic configuration of element with atomic number equals 90 is Rn 5f0 There are two unpaired electrons in the 6d orbital of the element. Hence, it is paramagnetic. Exercise Q3.01, page 191. Answer the following. Explain the trends in atomic radii of d-block elements. Solution. I. Atomic radii of the elements of the transition series decrease gradually from left to right. E. As we move across a transition series from left to right, the nuclear charge increases by 1 unit at a time. E. The last filled electron enters a penultimate N1d subshell. However, d orbitals in an atom are less penetrating or more diffused and, therefore d electrons offer smaller screening effects. IV. The result is that effective nuclear charge also increases as the atomic number increases along with a transition series. Hence, the atomic radii gradually decrease across a transition series from left to right. Trends in atomic radii of d-block elements. Exercise Q3.02, page 191. Answer the following. Name different zones in the blast furnace. Write the reactions taking place in them. Solution. Reduction, smelting. This step is carried out in a blast furnace. The charge-containing ore and limestone is introduced into the furnace through a cup and cone arrangement. In this arrangement, the cone enables uniform distribution of charge and the cup prevents the loss of gases. A blast of preheated air is introduced into the furnace below the Bosch. The charge and hot air come in contact with each other and various reactions take place. Chemical reactions taking place in different zones of the blast furnace. A. Zone of combustion. This is 5 to 10 m from the bottom. The hot air blown through the tires reacts with coke from the charge to form CO. The reaction is highly exothermic. Thus, the temperature of this zone is around 2000 K. Some of the CO formed dissociates to form finely divided carbon. 2CO right pointing arrow 2C plus O2. The hot gas rich in CO rises upwards in the blast furnace. The charge coming down gets heated and reacts with CO. Thus, Colorado acts as a fuel and also as a reducing agent. B. Zone of reduction 22-25 m near the top. Here, the temperature is around 900 K. Fe2O3 is reduced to spongy iron by CO. C. Zone of slag formation 20 m height from the bottom. The gangue present in the ore is converted to slag. This slag can be used for making a road foundation. The temperature of this zone is 1200 K. The gangue contains silica, alumina, and phosphates. Removal of this gangue is effected by adding limestone in the charge, which acts as a flux. Limestone decomposes to give Sao quick lime. D. Zone of fusion 15 m height from the bottom MnO2 and Ca3PO4 present in the iron ore are reduced to Mn and P. Some of the silica is also reduced to C. The spongy iron coming down in the furnace melt absorbs impurities like C, Mn, P, and S. This molten iron collects at the bottom in the furnace. The slag is lighter, floats on the surface of molten iron. Molten slag and iron are collected through separate outlets. Molten iron is poured into molds. These solid blocks are called pigs. This iron contains about 4% of carbon. When pig iron is remelted, run into molds, and cooled, it becomes cast iron. The waste gases containing N2, Colorado, and CO2 escape through the outlet at the top. These hot gases are used for preheating the blast of air. Exercise Q 3.03, page 191. Answer the following. What are the differences between cast iron, wrought iron, and steel? Solution. Cast iron, wrought iron, steel. I. Hard and brittle. I. Very soft. I. Neither too hard nor too soft. E. Contains 4% carbon. E. Contains less than 0.2% carbon. E. Contains 0.2 to 2% carbon. E. Used for making pipes, manufacturing automotive parts, pots, pans, utensils, etc. E. Used for making pipes, bars for stay bolts, engine bolts and rivets, etc. E. Used in buildings infrastructure, tools, ships, automobiles, weapons, etc. Exercise Q 3.04, page 191. Answer the following. Iron exhibits +2 and +3 oxidation states. Write their electronic configuration. Which will be more stable? Y. Solution. I. Electronic configuration of Fe2+. 1s22s22p63s23p63d6. E. Electronic configuration of Fe3+. 1s22s22p63s23p63d5. E. Fe3+ is more stable than Fe2+. This is due to the presence of half-filled d orbital in Fe3+. Exercise Q 3.05, page 191. Answer the following. Give the similarities and differences in elements of 3D, 4D, and 5D series. Solution. I. Similarities in physical properties. I. All D block elements are lustrous and shining. E. They are hard and have a high density. E. They have high melting and boiling points. IV. They are good electrical and thermal conductors. V. They have high tensile strength and malleability. V. They can form alloys with transition and non-transition elements. V. Many metals and their compounds are paramagnetic. V. Most of the metals are efficient catalysts. E. Similarities in chemical properties. I. All D block elements are electropositive metals. E. They exhibit variable valencies and form colored salts and complexes. E. They are good reducing agents. IV. They form insoluble oxides and hydroxides. V. Iron, cobalt, copper, molybdenum, and zinc are biologically important metals. V. They catalyze biological reactions. E. Differences. Although most properties exhibited by D block elements are similar, the elements of the first row differ from second and third rows in the stabilization of higher oxidation states in their compounds. Exercise Q 3.06, page 191. Answer the following. Explain trends in ionization enthalpies of D block elements. Solution. I. The ionization enthalpies of transition elements are intermediate between those of S block or P block elements. This suggests that transition elements are less electropositive than elements of groups 1 and 2. E. As the atomic number increases across a transition series, the first ionization energy increases with some irregularities. E. Ionization enthalpies for a given element increases from the first ionization enthalpy, i.e. 1 to the third ionization enthalpy, i.e. 3. IV. The atoms of elements of the third transition series possess filled 4f orbitals. 4f orbitals show a poor shielding effect on account of their peculiar diffused shape. As a result, the valence electrons experience a greater nuclear attraction. A greater amount of energy is required to ionize elements of the third transition series. The ionization enthalpies of the elements of the third transition series are, therefore, much higher than the first and second series. Exercise Q 3.07, page 191. Answer the following. What is meant by diamagnetic and paramagnetic? Give one example of diamagnetic and paramagnetic transition metal and lanthanoid metal. Solution. The substances with all electrons paired are weakly repelled by magnetic fields. Such substances are called diamagnetic substances. The substances with unpaired electrons are weakly attracted by the magnetic field. Such substances are called paramagnetic substances. Examples: transition metal, lanthanoid metal, diamagnetic, zinc, ytterbium, paramagnetic, titanium, cerium. Exercise Q 3.08, page 191. Answer the following. Why the ground state electronic configurations of gadolinium and lutetium are different than expected. Solution. Gadolinium and lutetium show different ground state electronic configurations because the 5d and 4f orbitals are near to the same energy due to which the next electron goes in 5d orbital instead of 4f orbital. This retains the extra stability achieved when the 4f orbital is half-filled and completely filled respectively. Thus, 5d orbital contains 1 electron in the case of gadolinium and lutetium. Exercise Q 3.09, page 191. Answer the following. Write the steps involved in the metallurgical process. Solution. The various steps involved in the extraction of pure metals from their ores are as follows. I. The concentration of ores. E. Conversion of ores into oxides or other desired compounds. E. Reduction of ores to form crude metals. IV. Refining of metals. Exercise Q 3.1, page 191. Answer the following. Cerium and terbium behave as good oxidizing agents in the +4 oxidation state. Explain. Solution. I. Cerium Ce and terbium Tb show +4 oxidation states. Their electronic configurations are given below. Ce equals Z 4F15D16S2, Ce4 plus equals Z. Tb equals Z 4F96S2. Tb4 plus equals Z 4F7. E. It is clear from the configuration of Ce that Ce4 plus is favored by its noble gas configuration. But it can be easily converted into stable Ce3 plus by a gain of an electron. Due to this reason, Ce4 plus is a good oxidizing agent. E. Similarly, Tb4 plus ion is stabilized due to a half-filled F subshell. It can be easily converted into stable Tb3 plus by gain of an electron. Due to this reason, Tb4 plus is a good oxidizing agent. Exercise Q 3.11, page 191. Answer the following. Europium and ytterbium behave as good reducing agents in the +2 oxidation state. Explain. Solution. I. Europium EU and ytterbium YB show +2 oxidation states. Their electronic configurations are given below. EU equals Z 4F76S2, EU2 plus equals Z 4F7. YB equals Z 4F146S2, YB2 plus equals Z 4F14. E. It is clear from the configuration of EU that EU2 plus is favored by its half-filled F subshell. But it can be easily converted into stable EU3 plus by the loss of an electron. Due to this reason, EU2 plus is a good reducing agent. E. Similarly, Yb2 plus ion is stabilized due to completely filled F subshell. It can be easily converted into Yb3 plus by the loss of an electron. Due to this reason, Yb2 plus is a good reducing agent.